Hi, welcome to Mechanical Engineering Thermodynamics. The topic of this video is the first law of reacting systems, and the sections in the textbook are 15.4 to 15.5. Here are the learning outcomes. At the end of this, you'll understand how different energy forms within a molecule are accounted for in this overall enthalpy term. You'll be able to determine the absolute enthalpy value of a reactant or a product at any arbitrary temperature. You'll be able to calculate the enthalpy of a reaction that is occurring at any temperature. You'll know what the adiabatic flame temperature refers to, and you'll be able to calculate the adiabatic flame temperature. So first what I want to do is I want to discuss absolute enthalpy. And so what we want, here's the question we're trying to answer. I want to know what the enthalpy is, for example, of carbon dioxide, and I want to know it at 350 degrees Celsius. And carbon dioxide is a product of a combustion reaction. And so I don't know what it is initially, or what I should say is it doesn't occur initially at a lower temperature. It is being produced at 350. Maybe it's being the product of burning of methane, for example. So I need sort of an absolute value for this. And the way that I do it is I come back to this idea of the enthalpy of formation. Remember, the enthalpy of formation lets me determine what the enthalpy is of a material, any material, at 25 degrees Celsius, and that's what this little degree symbol means, which is the standard state. And we define these components, these sort of building blocks, O2, N2, H2, and carbon, as having an enthalpy of formation of 0. Right? Now, if I wanted to go ahead and determine what the enthalpy of formation of CO2 was, I would take my carbon that has an enthalpy of formation of 0, and an O2 molecule, enthalpy of formation of 0, both of these at 25 degrees Celsius. I would break that bond, and then I would form these two double bonds, and then that would go ahead and give me what the enthalpy of formation is of CO2, and that would be at 25 degrees Celsius. Now I want to go ahead and take this from 25 up to 350, for example. And so what I'm going to do is I'm going to use this equation right down here where I'm going to take the enthalpy of formation value that I just calculated, and then this right over here is going to be my change in enthalpy from, for example, 350 minus it at 25. So those are going to be the two temperature changes. And in fact, these H values here are essentially just Cp times T. So I'm adding the formation component, and then I'm taking it to this new temperature up at 350. So whenever I want to find an absolute enthalpy value, I'll call it H absolute or maybe H total, for example, I'm going to have these three values, and I'm adding two components, the formation component and then the sensible change going from 25 Celsius to whatever temperature I want to go to. It could be higher than 25 or lower than 25. All right. So during combustion, one of the things is the temperature changes tend to be very large, several hundred to maybe thousands of degrees. And so when I want to know my enthalpy, so let me just write that equation again. I have H, which is HF plus H minus H0. These two values right over here often differ by very large temperature differences. And so what I actually want to do is I want to be going from 25 Celsius to some T high value. I want to be integrating Cp as a function of T times dt. And so I need to account for this variability in heat capacity. And so you could go ahead and stick in the equation, for example, from A to C, and do that yourself, but fortunately someone's already done it. And that's what's in these tables A17 to A25. So here, for example, I'm showing table A20, which is the ideal gas properties of carbon dioxide at CO2. And here's my enthalpy value. This is H. And this right there is just the integral of Cpt going from 0, actually, to some temperature T prime. And so that way you can go ahead and determine any of these two values. And so these are the H and H superscript 0 values. This value right there at 298, that's 25 degrees Celsius, that right there is H0. And then I can go ahead and look up, and this table goes on, and any of my H values at any of these other temperatures. And so what you realize, this table actually goes to several thousands of degrees. So you just go ahead and pull these two values right off of the table to go ahead and put it in that component. This one comes off of table A26, which is the heat of formation value. So let's go ahead and do an example, and I'll show you where this comes in. So the question is, I want to calculate the rate of heat release during the combustion of propane, and we say that the products are coming out at 300 degrees Celsius. We'll make another couple of assumptions. We'll assume that the temperature going in is equal to, for example, 25 degrees Celsius, right? And we'll also assume that it's complete combustion. So we don't need to account for excess air. We don't need to account for any incomplete combustion. The first step is to go ahead and balance my chemical equation. So I'm going to balance it for propane. Propane C3H8. And then I'm going to have my air, O2 plus 3.76 N2. Complete combustion is going to form CO2. It's going to form water. And it's going to form N2. So let's go ahead and balance the equation. 3 carbons on the left gives me 3 carbons on the right. 8 hydrogens on the left. That's going to give me a coefficient of 4 in front of the water. And so now I see I have 3 O2s and another 2. That's going to put me a coefficient of 5 in front of that air term. And now I can go ahead and balance the ends, and that's going to be 5 times 3.76. I need to distribute that. So there's my balanced equation. And now I'm going to go ahead and write my energy equation. And so the energy that's going in is going to be the number of moles of propane times the enthalpy of propane. If I'm using number of moles, I'll put a little bar. Those are going to be enthalpy per value, or per mole values. Plus, and then here I've got 5 times the enthalpy of O2, plus 5 times 3.76 and the enthalpy of N2. And that's everything that goes in. So that's going to be equal to everything that comes out. So I'm going to keep going. Now I've got 3, which is the carbon dioxide, the enthalpy of CO2, 4 times the enthalpy of H2O, and then 5 times 3.76 times the enthalpy of N2. And all of those are on a molar basis. Now for each one of these H values, remember this, each one of those H values is going to be HF, enthalpy of formation, plus H minus H0. And I'm going to determine that for each one of these values. Now, one of the things is that if I made this problem a little simpler by saying the temperature going in is 25 degrees Celsius, which is 298 Kelvin. And that means that on all the terms on the left-hand side, this value here is going to be the same as that. Which means all I need are the enthalpy of formation values, and the enthalpy of formation of O2 and N2 is 0. So it turns out I can go ahead and those first 2 terms are going to be a flat plus to 0. The only thing I'm going to have left is going to be the enthalpy of formation of propane, which is what's going to be left in here. And so what I have is for the enthalpy of propane, which is simply the enthalpy of formation of propane, and that value I get off table 1A126, and that's 103,850, and the units of that are kilojoules per kilomole. Okay, and since all these are in moles, each one of these will be per mole. Then the next 2 are 0, so now we've just got the terms left. For example, the enthalpy of CO2. So let's look at that. The enthalpy of CO2. Now this is at 300 degrees Celsius. So I got to account for all 3 because its enthalpy of formation is not 0. So first I have the enthalpy of formation. That is minus 393,520. And then I need to add this at 300, which is about 21,010. And then subtract it at 298,9364. Okay, so there's my 3 components for CO2. It's going to go into that one right there. I'm going to do something similar for water. I'll go ahead and skip that and let you do that one. The last thing to look at is this value for N2. Now, this one over here, I was able to say that it was 0 because it was at 25. So I had heat of formation of 0 and H minus H0 was 0. Those are going to cancel. But that's not going to be true when it's coming out at 300. So I need to have H of N2, and maybe think of an H to the N2 going out. 0 for the enthalpy of formation, but I need to account for its temperature change. So that is 16,762 minus 8669. So again, that value there is at 298, and this one right over here is at 300 degrees Celsius. So what I'm going to do then is to stick all these in, and so the amount of heat being produced is going to end up being Q, so I forgot to include my Q dot term. That's going to be the amount of heat produced when I burn per mole of propane, if I just do that in 1. And if I go ahead and put the numbers in there, and I'll let you look up the values for water to verify it, you get Q is equal to about 1.8 times 10 to the 6th, and the units of that are going to be kilojoules per kilomole of propane. So for each kilomole of propane I burn, I'm going to be producing this much energy, which is a lot of energy, but that's actually a fair amount of propane as well. All right, the next thing I want to talk about is the adiabatic flame temperature. And what that is the highest temperature that can occur when a combustion of a product. And so the way to think of it is, here I show this old Bunsen burner. So imagine this is burning propane, for example, like we just looked at. And if I was to do my energy balance right over a little box right there, Let me go ahead and blow that up and think about what that looks like. What I would have is essentially fuel and air coming in, and then I would have exhaust coming out. And it's a fairly little small, so there's no chance for heat transfer. So it's more or less adiabatic. We can say Q is equal to 0. And so now this is an open system. The energy going in is going to be the mass flow rates going in times the enthalpy going in. So I'll sum over that. Everything going in is going to be equal to the summation of the mass flow rates times the enthalpy of everything going out. So in is equal to out. And so essentially what goes in is the fuel. So what I end up having is the summation of the number of moles of reactants times the enthalpy of reactants is equal to the number of moles of the product times the enthalpy of the products. And so all these products here are going to be at some high temperature T2, which is the adiabatic flame temperature. It's the highest temperature that I can have. The other thing to assume is complete combustion. That's going to give you the highest temperature. And you assume stoichiometric or theoretical air. If you had excess air, you would end up having a lower temperature because you're going to be warming extra air that you're not using. And if you had less than that, you would have incomplete combustion, which would also result in the lowest temperature. So these two requirements here are necessary in order to get the highest possible temperature. So what I'm effectively doing is solving for T2 because that's what I don't know. All these products are going to be at that enthalpy value. So let's look at it. Let's calculate what the adiabatic flame temperature is of propane. And what I'm going to do is I'm going to move to EES and show you another way to solve these problems. And it makes solving for the adiabatic flame temperature a lot easier. Okay. So here I have my problem in EES, and let's look at it. And this is actually the previous problem I did. I'm not doing the adiabatic flame temperature first. I have T1, which was my input, which was 298 Kelvin. I have my unit systems in Kelvin. And then my output was at 300. I went ahead and just found all of my enthalpy values using the enthalpy function. And the enthalpy function, as I've written here in EES, is all three of those components, HF plus H minus H0. Well, it's pretty simple to do in EES. You just call it with the enthalpy function. Make sure to get ideal properties, you use the chemical formula in each one of these. Don't go ahead and write out the words. Otherwise, you'd be getting ideal gas properties, and it would require pressure for the enthalpy value. And then here was that energy balance that I had for the balanced equation. Where I was solving for Q. And so if I go ahead and solve this, here I have the solution to my problem, and I see there's my Q, which is 1.8 times e to the 6. Okay, that was a previous example. So if I'm going to solve for the adiabatic flame temperature, that means I don't know T2. So effectively, I'm just going to go ahead and delete that because I don't know what T2 is. Right? But also, I know that Q is 0, so I can effectively just delete that. And what it's going to do now is EES is going to implicitly solve for a value of T2 that satisfies my energy balance. Okay. So if I go ahead and do this and look at this, it found a solution, and it found a fairly strange solution of 1.3, which doesn't make any sense if this is in Kelvin, that the final temperature would only be 1.3 degrees Kelvin. The reason for this is this problem is fairly nonlinear. I need to put some constraints on this so it finds a solution that's in the right range. There's actually more than one solution to the problem, not solution to the thermodynamic problem, but one solution to the numeric problem. The way that you do that, go up under Options and Variable Information. Here's your value of T2, and look at it, it's guessing a value of 1. Well, we clearly know it has to be at least 298, or it needs to probably at least be 300. So we would set the limits. It's 300, and it might be as high as 3,000, I don't know. But I'm going to go ahead and put some limits on that value, and then I'm going to go ahead and calculate this and see if I get a new value that makes more sense. Now I see, here it is, T2 is 2391. That's a much more sane value, and that's what you expect for adiabatic flame temperature, on the order of a few thousand degrees, pretty hot. So there's kind of an extra step you need to go through sometimes to go ahead and put the constraints or limits on the variables when you're solving for the adiabatic flame temperature. If you're doing this by hand, it's a lot more work because you have to guess the value of T2, plug it into the energy balance, and iterate through. So you might find EES is a lot more helpful in order to do these problems. Okay, I want to talk about one last topic, and that is pre-ignition or pinging in an engine. So first, let me describe what is pinging in an engine. So here, this is a picture of a piston cylinder like in an automobile. This is a spark ignition system. Remember, the spark ignites it. So what happens is we have a compression, and then the spark, as the piston begins to go down, so that it expands. Pinging or pre-ignition means that the piston head is still going up, and then the combustion products go ahead and spontaneously burn even before the spark plug happens. And what that does, often the spark plug is a little bit offset. It causes the piston to twist a little bit because it's being pushed up, and then this explosion is causing hot gases to push down on it. This is pushing up. The piston turns to the side, and you have a couple contact points, which is the pinging noise that you hear. The thing that it becomes important is you want to know what is the temperature that's occurring inside here, because this actually can cause warping of your piston head. And so let's look at solving this problem. And effectively what I have is, because this explosion happens fairly quickly, is I have a constant volume system. And so what I have is, more or less, think that looks a lot like a rigid tank that has fuel and air in it, and then it spontaneously combusts, and it becomes a rigid cylinder of the same size, but it all has exhaust gases. So that system goes from there. So this would be at some time t1, and this is going to be at some time t2, just a fraction of a second later. No time for the piston to move. And so if I look at my energy balance, right, since there's no time for heat transfer yet, effectively what I have is a very simple energy balance which says the change in internal energy is zero. It's a constant volume tank. There's no boundary work going on. The change in internal energy is zero. And so what I'd like to do is be able to solve for T2. I want to solve for essentially the adiabatic temperature, but now I want it for using these values of U. And everything I've looked at so far has had values of H. Remember, we have H is HF plus H minus H0. And you might wonder, is there an equivalent U plus U minus U0? And it turns out there really isn't, but there's an easy way to go ahead and determine this. Remember that the definition of enthalpy is defined as U plus EV. Okay? And so if I was to go ahead and write that on a per mass or per mole basis, I'd have H is equal to little u plus PV. And if it's an ideal gas, I can go ahead and replace PV with RT, because in the ideal gas law, PV is equal to RT. So H is equal to U plus RT. And now I can go ahead and just say U is equal to H minus RT. Well, that's kind of nice, because now if I'm going to go ahead and do my energy balance, which says that the summation of the internal energy of the reactants is the summation of the internal energy of the products, since of the products there. And so for each one of these, this is just going to be H minus RT of the reactants is equal to the summation of H minus RT of the products. And so for each one of those, I'm going to sum over it. So for example, what I'm going to have is the number of moles, and then I'll have HF plus H minus H0, and then I'm just going to, each time, going to have to subtract an RT. And so this is going to be for each one of the components. So maybe I have for CO2 and for O2 and H2, each one, I'm just going to be having my enthalpy values and subtract some number of RTs. And what you'll see is you have a bunch of RT terms, all multiplied by the various coefficients, the number of moles. You can collect them all at the end and account for those that way. So this way you don't need to have internal energy values of formation. You can use your enthalpy values and just put in these values of RT.